to remind you, the type of symmetry that we're looking at with even and odd functions are easy to remember if we think about an even function would be, you know, similar to an even power function, like f of x squared, for instance, is an even function because it has the property that f of negative x and f of x, right? Flipping the graph in the y-axis doesn't change the graph. So we have the symmetry with respect to the y-axis. Okay, and you can imagine here if we've got the graph of y equals x squared, that would be an example, or any graph really that has that type of symmetry. Here, better. So actually you can something like that, and it's just the same on the left side, right? So symmetry. So this is what an even function would look like. It has this type of symmetry. An odd function has the opposite property. This is a different type of symmetry. We say this is symmetric with respect to the origin. Meaning if we rotate the curve 180 degrees about the origin, we get the same curve. So it's sort of like a rotational symmetry. So if I have a graph like this, maybe on one side it looks like this, and rotating that around would give me something like this on the other side. So what we want to think about here is how the area compares to the left and the right side of the graph. For instance, if I'm looking at, say, the left and the right side of an even function, we notice that here the areas above and below the x-axis, if I go, say, a distance negative a to the right, positive a to the left, or sorry, negative a to the left, positive a to the right. Essentially, the left and the right-hand side are going to equal, have equal areas that are bounded by the graph. Versus if I have an odd function, it's kind of the other way around, where from negative a to a, they're the same distance away from the origin on either side, the areas are going to be opposite in sign, so they cancel out. So in either case here, we get some symmetry that we can exploit. When we have an even function, the area to the left and to the right are equal, so we can just find the area to the right and then double it. So the integral from negative a to a of f of x is equal to 2 times the integral from 0 to a. Since they're the same area on either side, when we have an even function at least, then we can exploit the symmetry by just integrating from 0 to a and then multiplying it by 2. For an odd function, though, it's even better because now the area on the left and the right are going to be opposite in sign. So if I have an odd function, then we see the integral from negative a to a would be essentially opposite in sign from negative a to 0 and from 0 to a. So those two regions will have opposite sign that cancels out. So the integral from negative a to a for an odd function will just be 0. So that makes evaluating certain integrals when we have the limits of integration look like that. They're from negative a to a. So there's that symmetry with the limits of integration. then we can oftentimes exploit the symmetry in the functions as well. So let's think about some examples with that. So yeah, here's the theorem, but it's sort of what we observed in the graph, right? But let's just practice with some examples. So if I want to evaluate the integral from -2 to 2 of x to the fourth minus 3x cubed. Notice that individually, each term here is a different type of symmetry. Like the first term, x to the fourth, that's an even function. And then the second term, 3x cubed, is an odd function. So if we want to exploit symmetry, we should look at each term separately. So I'm going to actually integrate from -2 to 2 x to the fourth, and then minus 3 times the integral from -2 to 2 of x cubed. Because now here we can exploit the symmetry. We know x to the fourth is an even function, has that even symmetry. X cubed, on the other hand, is an odd function because it has the odd symmetry. So using the rule that we just established, the integral from -2 to 2 for an even function will be 2 times the integral from 0 to 2. For an odd function, it's going to be 0. Right? So then I just have to do 2 times the integral from 0 to 2 of x to the fourth. So now that's sort of simplified the amount of work that I have to do to evaluate this integral. So we get 2 times, let's see, this will be x to the fifth over 5. And then from 0 to 2. And now what's nice is that when I evaluate it at 2, I get, let's see, that will be 2 times 32. And then when I evaluate it at 0, I get 0. So that makes it easy to evaluate it at the other endpoint. So it's just 64 over 5. In this other example,
Professor?
yeah, go ahead.
In this second line for part A, where did you get the 2? Like the 2 where it's like the 2 squiggly line 2 0 x to the fourth d of x minus 3 times 0.
So yeah, so there I'm just using the fact that this is an even function. So let's remember, if I have an even function, the rule that we just established is that this is equal to 2 times the integral from 0 to a. When f is an even function. Okay. So that's what I'm using here. If you want to picture it, imagine what the graph of x to the fourth looks like. It's like this, right? It's like almost like a parabola. So if I'm going from -2 to +2, the area from this side and this side really are the same area. So I can just do 2 times the integral from 0 to 2. Okay. That's just using this first property here. Okay. And then this one is using the odd function property in part B. All right, I mean in the second property. Right? So the integral from negative a to a is 0 when f is an odd function. Okay, so what kind of symmetry do we have with part B? I'll look at each term separately again. So for the first term, negative pi over 2 to positive pi over 2 cosine x. And then minus 4 times the integral from negative pi over 2 to positive pi over 2. What kind of symmetry does the graph of cosine have? Is cosine an even or an odd function?
Odd function.
So think about what the graph of cosine looks like. Right, cosine starts at 1, 0, 1, and then it kind of oscillates from there, right? Is this even symmetry or odd symmetry?
That'd be even symmetry.
So this is an even function, right? So cosine is even. And sine x, remember, is an odd function because the graph of sine looks more like this, right? It goes up from the middle, and then on the left side, it's the opposite. So yeah, so we see sine is an odd function. And actually, the same would be true for sine cubed, the power of 3. So, so if sine is odd, we know that sine of negative x is equal to negative sine x. So it'd be the same for sine cubed. Sine cubed is also an odd function. So sine cubed is an odd. So here we have an odd function. Here we have an even function. So now I'm going to use the even function rule, which says the integral from negative pi over 2 to positive pi over 2 will be 2 times the integral from 0 to pi over 2. And then the odd function rule is that the integral from negative pi over 2 to positive pi over 2 for an odd function will just be 0. So that makes it easy here. We can just integrate cosine, what we know is sine, and evaluate from 0 to pi over 2. So we get 2 times sine of pi over 2 minus 2 times sine of 0. Sine of 0 is 0, sine of pi over 2 is 1. So it's just 2. Okay, so that's a nice little property that we can exploit here when we notice that we have integrals that go from negative a to a. Notice that it requires that that symmetry in the limits of integration, that from negative a to a, so it has to be of that form, like negative 2 to 2, like we see here, or negative pi over 2 to positive pi over 2, like we see here. Okay. So I want to think about the average value for a moment. This is the other thing that our other goal for this chapter, I mean for this section, I should say, is to think about the average value of function. So let's just take four values, or sorry, five numbers here. So to find the average of five numbers, we just add them. And in this case, we divide by 5. And yeah, whatever, we get something here for the average value. Let me just throw that into my calculator real quick. Maybe something around 141.2. Okay, but this is just looking at 4 different values. If we have a function, say f of x on some interval a, b, this is not just a collection of points, it's actually infinitely many points. So if I'm thinking about how would I find the average value of these infinitely many points, well, let's think about how we would approach it with something that resembles a Riemann sum, right? So we partition the interval a to b, like we see here. We know that since delta x is equal to b minus a over n, we can write n is equal to delta x over b minus a. So that sum of all those function values in the partition sorry, b minus a over delta x is what I meant here. Sorry, I wrote that upside down. Which we can think of here as really just 1 over b minus a. And then we've got some of these function values times delta x. So it's really 1 over b minus a times this Riemann sum. And so if we want to get it for all these infinitely many values, we can take the limit as n goes to infinity. We'll call this f bar. And so that's, maybe notation that resembles the notation we would use for the mean of a sample like this. So x bar would be what we use here, but for the average of a function, we use f bar. And what we notice is that when we take the limit as n goes to infinity, this just becomes the Riemann sum of an integral. So it's 1 over b minus a times the integral from a to b of f of x. So finding the average value of a function, is just doing the integral from a to b. So we're finding the average value of the function on an interval a, b. So it's finding the integral from a to b of f of x and then dividing by b minus a. Okay, and what you can observe here is that the way we think of it is the average value is really this value that's sort of in between, maybe you can imagine it's in the middle of all the function values here. So if our function takes on values here between a and b, so f and our average value is going to be somewhere in the middle of all those function values. And the way we've defined it, it looks like here the average value, whatever that is, we imagine that the height of that rectangle here, where f bar is the height of that rectangle, would have exactly the same area as the area under the curve, right? So the area from a to b under the curve of f of x is equal to the rectangle that's formed here, where f bar is the height of that rectangle. So we see in this case the rectangle here, area of that rectangle, has the same area that's under the curve. Okay, so the area under the curve is equal to the area under the rectangle with a height of f bar. So the area under the curve on that interval AB. That makes sense here because of the way that we've defined f bar, right? If I multiply b minus a times f bar, we get the integral from a to b. Okay. So you can imagine it's just like maybe I flatten out the curve, sort of fill in the area, just like take a bulldozer and flatten it out. That's what we get. The height of that flattened region would be our average value. Okay, so let's think of an example here. A hiking trail has an elevation given by f of x equals 60x cubed minus 650x squared plus 1200x plus 4500, where f is measured in feet above sea level, and x represents horizontal distance along the trail in miles. In this case, x going from 0 to 5. So what is the average elevation of the trail? So we're just going to compute f bar here. And we're only on the interval from 0 to 5, so we'll do 1 over 5 minus 0, and then integral from 0 to 5. So I'll have 1 over 5. And then integrating here, we get, let's see, 60x to the 4th over 4. Minus, let's see, this will be 650x cubed over 3. $1,200 x squared over 2, and then 4,500x. And evaluate from 0 to 5. Okay, so actually, some simplifying that can happen here. Actually, let me, I'll do a couple things. I'm gonna simplify the coefficients, and then I'm also gonna divide by 5. So I'm gonna multiply the 1/5 into the parentheses here. So let's see, if I do 60 divided by 4, divided by 5, I get 3 here. So this will be 3 times 5 to the 4th. 650 divided by 3 divided by 5. So, well, actually, I'll just write this one as 130 over 3, 5 cubed. This will be 120 x squared, or 5 squared. (900) times 5. Okay, and then evaluating them all at 0 will just be 0 for all of them. And then just kind of simplifying these a little bit. Get something around 2,708.33 feet. So this would just represent the average elevation over the first 4 miles, or sorry, first 5 miles of this trail. Okay, so you can imagine that the trail itself maybe is going up and down. So this value would be somewhere in the middle of all that. So yeah, here you can see exactly where that lies. So you got something that maybe is going up at first and then starts to decline. Okay. And I must have made a mistake somewhere, because here it looks like their average elevation is close to 4,000. Ours was a little bit lower than that. So I probably made a mistake somewhere calculating it. Maybe you guys can help me spot it. Or did I make a mistake?
I think it was worth 625. Forgot to multiply it by 3.
Okay. Yeah, 5 to the power of 4, 625 times 3. Yeah, so 1875. Okay, yeah, that gives me something closer to what it looked like in the picture. About 3,958.33. Okay. Now looking at the picture, we get, yeah, that looks about right. The average elevation here would be somewhere in the middle of all those different elevations.
Professor, could you go back to the left side for a second? Thank you.
Alrighty, so that's the average value, and we have a version of the mean value theorem. And if you guys remember what the mean value theorem said before, it said something that like our function will have a point where f prime is equal to the slope of a tangent. But here we can think of the mean value theorem for integrals looks more like the picture that we have here, where we see that our average value is like this straight line, or I mean this horizontal line here, and we see that it has to intersect the graph at a point. So our variation of the mean value theorem for the average value when we're looking at the integral, so it's like a mean value theorem for integrals, says that, yeah, our mean value, there's going to be a point somewhere on the graph where the mean value intersects with the graph. So the graph is going to, or the function is going to equal to the mean value somewhere on the interval. So here's the picture again from before. We see that the graph looks like this. Integral from a to b would be the area under that curve, and then the mean value was the area under this rectangle. And what we see is that there's some point where, say C here, where the average value, where the function is equal to the average value. Right? So some point C where f of C is equal to f bar. Right, so here's the way we can say it here. So if f is continuous on the interval a, b, then there exists a point C in the open interval a, b, such that f of C is equal to f bar. Okay. And just to kind of compare this with the mean value theorem that we had before, says that if f is continuous, so it actually needs to be continuous and differentiable. Remember, because we have to be able to find a derivative. In this case, notice it doesn't have that differentiable requirement. So if we kind of look, if we compare this, notice that here this requires f be differentiable so that we can find f prime of c. We know that that's guaranteed here. But if I were to just integrate the two sides of the equation, well, we can imagine here, we know that in general, the integral from a to b of f prime of x is equal to f of b minus f of a. And then if I put 1 over b minus a here, you actually do kind of get a very similar looking version of the theorem here. But anyway, so this is just a variation of it. Just says that, yeah, the average value, so f of x is equal, I'll just say f of c, or f of x is equal to f bar for some value. So let's actually try that out. So find the points on the interval 0, 1 at which f of x equals 2x times 1 minus x equals its average value on that interval. So let's go through and we'll compute the average value here. So f bar would be 1 over 1 minus 0, and then integral from 0 to 1. And then our f of x is 2 times 1 minus x. Okay, so this one actually is just 1 over 1, so that's not really changing anything there. Integral from 0 to 1 of 2x minus 2x squared, which will be, when we integrate, 2x over 2x will be 2 times x squared over 2, so it'll just be x squared. And then integral of x squared will be x cubed over 3, so that'll be minus 2x cubed over 3. And then evaluating from 0 to 1, we get 1 minus 2 over 3, and then minus 0. So it just becomes 1 over 3. So that's our f bar. So the mean value theorem guarantees there is a solution, there is a point C in the interval 0 to 1 where f of c is equal to 1 over 3, right? Where f of c is equal to our f bar that we just computed here. Okay, so let's actually solve for that point C. So we'll just take our original f here and equal it to 1 over 3. Which will just be 2x minus 2x squared. So to solve this out, what might help here is I can maybe rearrange some of the terms here. You see, it's just a quadratic equation that maybe we can use the quadratic formula to solve for if we need to. Unless it factors, I'm not seeing if it factors or not. But yeah, it's kind of hard to do in my head, but we can just solve it out using quadratic formula. Just putting everything into the quadratic formula. Let's see. So that would be 4 minus 4 times -2 times -1/3. 4 minus 8 over 3, which would be write that out so I don't mess that up. So that'll be 24 minus 8 is 16. So we get 16 over 3. Yeah, so it'd be -2 divided by -4 is 1/2, plus or minus, this will be the square root of 16 is 4 over square root of 3, and then dividing by the 4. So I think it would just be 1 over the square root of 3. And let's just verify quickly that those values are in fact in the interval, or at least one of them is in the interval because we get two solutions here. Let me see, I'm getting something not quite right.
Is it because it's 16 over 3 in the radical?
I'm sorry, could you say it again?
How did you get 16 over 3 inside the square root?
How did I get that? Oh yeah, I think I made a mistake there. Let me double check that. So that should be 4 minus, so that's 12 minus 8. Okay, yeah, that's where I made a mistake. Thank you. So yeah, 12 minus 8 is 4 over 3, right? So then the square root of 4 is 2 over the square root of 3. And I got 2 over 4 will reduce to 1 over 2. Okay. So yeah, so let's just verify that this gives us something that we can use here. Okay, yeah, so that's good. So this gives me both of these values are going to be in the interval from 0 to 1. So it's 0.211 and 0.788. Or I'll say 789. Okay, so both of these are in, both solutions are in. Are in the interval 0 to 1, like it guarantees, like the theorem guarantees that at least one of them is in the interval. In this case, both of them are. Okay. Alrighty. Any questions?
Pretty much the like the line's gonna be on either of those 2 points.
Yeah, so if you want to picture what this looks like, you can imagine here we've got between 0 and 1 is going to be, I think this is going to, maybe you can see that it passes through 0 and 1. It's like this upside down parabola, maybe something like this, right? So 1/3 would be right around there. So it's going to hit the graph at those 2 points, right?
Oh, okay, I see.
Okay. So yeah, I think that was all we wanted to say from that section. So yeah, that section is not too much going on, just a couple of new ideas, but we can maybe quickly just get it set up for the next section, which is a little bit more going on. Because now our goal is to start thinking about more complicated antiderivatives, or evaluating more complicated antiderivatives using substitution. So yeah, so we kind of have like a chain. You remember, if we've got like a function inside of a function, we know that the derivative, we have like a chain rule for that, right? Sorry. So to do the antiderivative, well, we're going to start to think about how we can reverse the chain rule here. So it's like the integral of something that looks like this will be that composition f of g of x. So it's kind of like we're reversing the chain rule. Okay, so that's kind of what substitution rule is. We want to think about how we can find these functions inside that we can replace with, say, a simpler expression to make it easier to find the antiderivative. So that'll be how we're going to approach it here, is that we're going to replace that inside function with a different variable u. So it'll look like this. If I let u equal to the inner function here, and this is like our inside function. Which is g of x. Then the derivative of u, we can think of now, if I compute the differential for u, we'll just be taking the derivative, g prime of x dx. So this guy here, when we do this kind of substitution, this becomes our differential, du. Okay, so that's how it transforms it into the integral of f of u du. So our goal is to get something here. Now this is maybe it's easier to find the antiderivative with respect to this variable. It looks more complicated on this side, so simplifying it like this, maybe it's easier to find the antiderivative. Okay. So let's think about just the process that it's going to require. So we're going to look at an integral and try and figure out what the inside function is that we want to replace with some variable u, some new variable u. So it's like we're changing the variables from x to u. And we want to choose u carefully because we want it so that the derivative of whatever we choose for u is somewhere in the integral also, right? So we want to identify an inner function u equals g of x such that a constant multiple of g prime of x appears in the integrand. Okay, so then we're going to replace g of x with u, and then we're going to replace g prime of x dx with du. And hopefully we get something that's easier to evaluate with respect to the variable u. And then after integrating it, then we can put our u back in. Okay, and there are disclaimers that not all integrals yield to the substitution rule. In other words, there may be other tricks that we'll need to think about later on. But here we'll hopefully try and look at a couple different ways that we can get our integrals to work out with the substitution. Let's just do a simple example here, and then this is probably what we'll have to leave it today. We can finish the rest up tomorrow, but I just want to demonstrate quickly how this rule works. So in this case, there's clearly this inside function 2x plus 1. So let's call that u. If I'm going to let u equal to 2x plus 1. Now this is a good choice because we notice that the derivative is just 2 times dx. And I see that here we've got 2 dx right there. So 2 dx, that's our du. So just with that simple substitution, the integral now is just u cubed du. And now it's very simple to find the antiderivative of u cubed. It's u to the 4th over 4. And now I can put my u back in. There we have it.